A pure sine wave is perfectly predictable. You know exactly what it will do at any given point in time. But natural phenomena, turbulent bursts, financial crashes, mechanical failures, rarely operate in uniform cycles. The pattern fractures. A localized, violent anomaly disrupts the system. To analyze oscillatory data, we traditionally rely on Fourier analysis. By decomposing a signal into infinite global sinusoids, Fourier analysis identifies exactly which frequencies are present. However, because those sinusoids stretch across all of time, the transformation discards the information regarding where those frequencies occur. This is the raw ink tracing of the 1923 Japanese earthquake seismogram. Here, temporal location is the most critical piece of data. Fitting global sinusoids to these localized bursts produces a messy spectrum, overwhelmed by overlapping waves compensating for the shock. This friction is governed by the Heisenberg time-frequency trade-off. In 1946, Dennis Gabor proved a signal cannot be localized strictly in both time and frequency. Zooming in to isolate the moment an event happens blurs its frequency. Locking on to its frequency loses its position in time. Solving this localization problem requires an analyzing waveform strictly confined in space, one that we can shift across the timeline and stretch to match specific scales. This is the architecture of the wavelet. The continuous wavelet transform approaches a signal by correlating the data with a localized atom rather than an endless wave. This equation defines the mother wavelet, controlled by translation and dilation. The translation parameter slides the wavelet across the timeline, correlating the atom with isolated events. The dilation parameter scales the atom. Increasing it stretches the wavelet into a broad window capturing macroscopic trends, while shrinking it compresses into a sharp spike catching sudden transients. Deleting factor, 1 over the square root of A, is a normalization term. It ensures the analyzing atom's energy remains constant, regardless of how it is stretched or compressed. Calculating this across every scale and position produces a two-dimensional scalogram. This logarithmic tiling captures physical signals more closely than the rigid grid of a short-time Fourier transform. While effective for visualization, calculating the transform for every continuous scale and shift produces massive redundancy, making it inefficient for scalable algorithms. To eliminate this redundancy, we restrict our scales and positions to a structured, discrete, dyadic grid, scaling exclusively by powers of 2. This is the basis of multi-resolution analysis, or MRA. It organizes data into a nested hierarchy of approximation spaces, moving from coarse structure to fine detail. This translates into a filter bank algorithm. An incoming signal splits into 2 pathways. The top applies a low-pass filter for coarse approximation. The bottom applies a high-pass filter, isolating sharp detail. Both branches are then downsampled by 2, maintaining linear complexity. This efficiency is paired with a specific filter property called vanishing moments. When this filter sweeps across a smooth, continuous region of data, the detail coefficients drop to 0. The filter only activates when it encounters a rupture, a jagged fault line, or a sharp edge in the data. This property guarantees mathematical sparsity. Because smooth regions are discarded, the defining geometry of a complex object concentrates into a small handful of non-zero coefficients. We see this directly in medical imaging. The black, empty spaces in an MRI scan require almost no data to represent. The wavelet concentrates computational power on the complex boundaries of the cranial structures. MRA functions as a structural engine. It separates chaotic edge information from smooth backgrounds to isolate the underlying mathematical truth of a signal. Classical wavelets require a rigid grid to define translation and dilation. However, modern scientific data, social networks, point clouds, and molecular graphs lives on irregular topological domains where a standard spatial grid does not exist. The spectral graph wavelet solves this by discarding physical distance. Instead of dilating an atom in physical space, we dilate it across the graph's spectral eigenvalues. We characterize network connectivity using the graph Laplacian matrix. We place a localized impulse on a single vertex and apply a spectral bandpass filter. The filter diffuses outward across the irregular connections organically, mapping the local cluster. We achieve translation by selecting different starting nodes and dilation by adjusting the power of the spectral operator, bypassing the constraints of Euclidean space. Redefining the wavelet as an operator rather than a fixed shape allows multiscale analysis on any topological domain. This is the foundation of geometric deep learning. Standard convolutional neural networks learn filters from scratch. While accurate, they lack provable mathematical stability. Small input deformations can significantly change the output. The scattering transform addresses this by replacing learned filters with a rigid, predefined cascade of wavelet operators. This architecture structures a scattering network. First, the input passes through a fixed wavelet convolution to separate structural frequencies. Second, a modulus nonlinearity strips the complex phase while preserving the amplitude envelope. Third, a low-pass filter averages the result, creating local invariance. High-frequency detail loss during averaging is recovered by passing the signal into the next cascading wavelet layer. Because these filters are mathematically constrained, the scattering transform provides stability against translations and deformations that standard neural networks cannot guarantee. These principles are now being used to solve partial differential equations in computational physics through wavelet neural operators. Instead of mapping finite pixels, wavelet neural operators project network weights into a multiscale wavelet basis. This tracks complex fluid dynamics and shock waves. Embedding wavelets into deep learning enforces the structural priors required to model physical reality, combining the flexibility of AI with the rigor of harmonic analysis. The goal of these advancements remains consistent: multiscale structural clarity. These panels represent distinct environments, from continuous scalograms to spectral graphs and neural operators. These diverse implementations share a singular mechanism, systematically partitioning coarse global structures from fine, localized details. They isolate the geometry of a dataset while strictly preserving its spatial relationships. This localized geometry provides a stabilizing framework for organizing chaotic data. The wavelet transform acts as a foundational mathematical operator, making multiscale reality computationally explicit. Modern computational science often attempts to solve complexity by feeding unconstrained data into opaque black box models. As scientific machine learning scales to model complex physics, wavelet transformations provide the geometric priors necessary to keep our algorithms grounded, interpretable, and mathematically sound.